Good afternoon. I am Philip Christian Sisuniga. I am a faculty member from the Department of Computer Science from the University of the Philippines, Diliman. Today is the third part of our webinar series on the development of a proof of concept health enterprise service bus for the Philippine Health Information Exchange. Just to give you a background, during the past two webinars, we discussed some components of our previous engagement with the Philippine Ministry of Health. During our first talk, we discussed how we benchmark enterprise service bus. So we benchmark the enterprise service bus that we will be using for the prototype. During the second part of my talk, I discussed the development of a design, the requirements, and the architecture for a health information exchange. So for today, I will be discussing the test that we conducted on the prototype. From our perspective, the test that we conducted is the most important part of our workflow because it gave us an idea on how the ESB will work. The test also gave us some performance benchmarks, and well, we were able to contribute some information to the Philippine Department of Health with regards to their actual implementation. So the tests that I will be discussing for today are the functional tests that we conducted, the integration test, and the performance test that we conducted. Basically, the idea in a functional test is we will be testing the production level code. We use a cloud setup. And the goal is to test the different functionalities of the ESB. In our functional testing, we try to isolate each functionality and test each functionality as a standalone functionality. So we wanted to be sure that each of the functions or the modules that we included in the ESB are working. So how did we perform the functional test? We have here a diagram. So if you were listening to my previous webinar on the requirements for an ESB, basically the requirements that we were able to obtain were the ESB should be able to authenticate, validate, transform, translate, perform migration, and route data. So the requirements that we were able to gather before serves as the basis of our functional testing. We wanted to test each of the functions in the ESB. So the first thing that we test, of course, the basic thing is that if we will check if the service is available. So how do you know if the ESB is available? So we send a request to the service or we ping the service and it must return a response. So that is the way on how we check if the ESB is up or not. Next, how were we able to test authentication? Well, the goal of testing this is we want to test if the service can authenticate valid users. So in authentication testing, we had two steps. First, we send an encrypted message using the correct key. So this is the valid step. So if we perform that, the ESB should not give us a response because it is a valid step. It means that the data encrypted must be forwarded to the next functional component. On the other hand, if we send an encrypted message using an incorrect key, this means that this is an invalid move. So the ESB must respond to us an error. In our set of responses, response 102 pertains to wrong encryption error. So the responses that we use are similar to the responses that are being used by the Ministry of Health in their own PHIE Lite. So the PHIE Lite is like a web service application that acts like an ESB. Next, we also want to check if the service can validate the data sent to it. So again, we have two steps. Number one, send a data that is valid based on the schema. So it is a valid data. Again, if we send a valid data to the ESB, there will be no response because it means that the validated data will be forwarded to the different components. On the other hand, if we send a data that is not valid based on the schema, then the ESB must return an error 103 or response 103. Again, the code, the response code is based from AeHIN Lite, so the local enterprise. The web service application that is used by the Philippine Ministry of Health. Next, we also check the transformation of data. So in checking for the transformation of data, we want to check if the service can produce an XML file or if the service can produce a JSON file. So because we wanted to be sure that we can cater to whatever data format requirement that is required by the registry. So how do we test that? So well, we send the data. So in our implementation, we considered JSON file, XML file, and CSV files. So we send the data regardless of the format, and we check if the output is an XML file. So it means that the ESB can produce an XML file. Similarly, we send another data, regardless of the format again, the ESB must produce a JSON file. So we wanted to test if the ESB can produce different formats or can convert an input format to another format. We also want to test the translation capability. For translation, we use an AeHIN terminology service to test if the ESB can work with a terminology service. So we wanted to know if a certain terminology from one system can be mapped to another terminology to another system. So how do we do that? We map two terminologies using the terminology service, so using AeHIN, so we map two terms, and then using the ESB, we check if they correspond with one another. So the ESB must indicate that the terminologies can be mapped to one another. Similarly, we send two data to the ESB, and these two data are not mapped in the terminology service and in the terminology service. So we want to check if the ESB can know if these two data are not mapped together, and the ESB must indicate that the two data the two terminologies are not mapped. Next, mitigation. Mitigation or service orchestration is a big functionality. So in order for us to test it, we followed the workflow that is being used in the primary health care workflow that is being used in the Philippines. So in our sample workflow, a patient who has some symptoms goes to a primary care physician. Usually this is a health clinic. And then the primary care physician will try to diagnose the patient. If she determines that the patient has a particular disease, and that disease is being monitored by the Philippine Ministry of Health, for example, diabetes, tuberculosis, cancer. So if it was diagnosed that the patient has those diseases, then the health worker must be able to report that instance to another registry. So in the ESB, what we did is if a health worker submits a health record, and in the health record there is a diagnosis of a particular disease, then the ESB will automatically generate a report, and that report will be submitted to the corresponding disease registry. So that is our mitigation workflow. So in order for us to test it, basically what we did was we sent an encounter data that should produce an incident report, and we check if the incident report was generated. Similarly, we send a data that will not generate an incident report, and the expected response is there should be no incident report that will be produced. So for routing, basically, we send a data to PHI if the data must be sent to the PHI Lite registry. So basically, this is content-based routing. If a data must be sent to the PHI Lite registry, then we will check if the PHI Lite registry will respond. Or if the data must be sent to the ICD NRS or the incident or the disease incident registry, then the expected response must be a response from the integrated disease registry. So that's how we tested the routing. For queuing, we wanted to know if the ESB can process concurrent requests. Take note that that the ESB that we use, the SATO ESB, has a load balancer in the software package. So we wanted to test if the load balancer was working. So in order to test if the load balancer is working, we tried sending concurrent requests to the ESB. We use SOAP UI to test concurrent requests to the ESB. And what is the expected response? The ESB must process all those requests. So we look at the logs of the ESB, and we check if all of the requests, all of the concurrent requests were processed. So during our functional testing, we were able to test all the functionalities, and all the functionalities passed the test. It means that the expected response were satisfied. Next, we also did integration testing on our ESB. So basically, when we say integration testing, this is an end-to-end testing of the ESB. So from the EMR to the ESB to the PHI Lite registry and back. So the objective of integration testing is we must be able to show the following. The EMR must be able to connect to the ESB. The EMR must be able to send data to the ESB. The EMR must be able to process data. Sorry, the ESB must be able to process the sent data. The ESB must be able to send the data to the registry. The registry should be able to send a response to the ESB. And finally, the ESB must be able to send the response back to the EMR. So that is the whole end-to-end workflow for our integration testing. For precondition, the EMR that we tested should already be able to submit to PHIE Lite. So as mentioned earlier, the PHIE Lite serves as the interoperability layer for the Philippine Ministry of Health right now. So it has web services. So what we did was we changed the workflow. Instead of the EMR sending to the PHIE Lite web service, it should send to the ESB web service, the ESB service that we expose. To simplify the use case for the EMRs, we followed the standards and the workflow set by PHIE Lite. We also followed the encryption and decryption mechanism used by PHIE Lite so that the EMRs will no longer need to adjust. It only needs to change the service that it is calling, that it is invoking. So we have here a sample EXP client. So this is the client that we use to send data to the ESB. So we have a web service key, an encryption key. We have here the URL where the ESB will be pushed, and then we initialize a hope client. We define the method. The parameter basically is the data. So we SL it inside the own, and also we SL it if it is on an standalone JSON file. We encrypted it using AES 256. We converted it to base64, and we send it to the ESB. And then it will send a response, and the response will be sent back to the EMR. So basically, this is the diagram for the integration testing. So the data will be encrypted using the EMR key pair. So the EMR key pair will be coming from the ESB. On the other hand, the data from the ESB to the registry must be encrypted using a different key pair. So we will call this the ESB key pair. So the response has, as mentioned earlier, response 102 means that the authentication failed. Response 103 means wrong parameter, so it cannot be wrong format, wrong validation. So those are the possible issues on why we receive a response 103. While response 104 is success. So again, we have a checklist. When we perform the integration testing, we had a checklist so that it is easy for us to determine if the ESB is working or not. So the checklist basically follows the steps that we indicated earlier. So we check, is the AMR able to call the service, or is it able to invoke the service? Did the ESB receive an encrypted data using the encrypted key? So basically, the integration test mirrors the same test that we performed during the functional testing, but this time we are not interested with particular functionalities, but we are interested on the whole ESB to PHIE Lite to EMR connection. So we are looking at this as a single system and no longer as individual functionalities. So tests were done on actual EMRs and the PHIE Lite registry component, and we were able to get a satisfactory rating on all the test items. Next, we also performed performance tests on the ESBs. Basically, the goal of the performance test is to determine the benchmark parameters for the ESB. So each experiment was simulated for 100 times, 100 consecutive times, where the results were averaged so that we can eliminate the variation in the result. So we recorded the response time and the processing time. To differentiate, the response time is the time when the request was made to the time a response is received. So this is measured from the size of the EMR. So this is the time. This specifies the time when the EMR sends our data to the time that it receives a response from the ESB. The processing time, on the other hand, indicates the time when a request was accepted by an ESB to the time a response was received by the EMR. So basically, the processing time measures the time that when the data is processed by the ESB, and then the data is sent to the registry sends a response, and then the ESB sends the response to the EMR. The bulk of the processing time is actually on the ESB side. Okay? So what is the difference between the response time and the processing time? Basically, if we receive concurrent requests, then the tendency is for the request to queue in the load balancer. So the response time measures the queuing time is included in the response time because the time when they are queuing it will be counted. On the other hand, the processing time, so the processing time is measured only at the time when the request is already received by the ESB. So it is already after queuing. So why do we need to differentiate between the two? We will see later in our queuing experiment. So the parameters that we considered are mean response time, so the average response time, mean processing time, so the average processing time, and the number of transactions per second. So basically, the transaction per second is just an inverse of the response time. We just wanted to measure how many transactions the ESB can process in a second. So what were the issues that we faced? Number one, we encountered internet connectivity issues during testing. Since all our setups are via the cloud, it is possible that the internet connectivity becomes an issue because data is sent via the internet. So we noticed that there were experiments that were taking a lot of time. Well, there are also experiments that were not taking a lot of time. We were able to deduce or to see that mostly if we conduct our experiments during the day, then the results, the ESB seems to be slower. On the other hand, if when we run the experiments during the night, the ESB seems to be faster. So what we did was we divided the experiment and we conducted the test during the night at basically more or less at the same time. So we predict so that we can have a more or less constant internet connectivity. Also, we tried deploying the ESB on the server, and we noticed that if there are many users in the server, the processing of the ESB takes longer, as versus the case when there are no users on the server, the ESB seems to work faster. So what we did was we deployed the ESB on a cloud server, and the cloud server is dedicated for ESB use only, so that we can be sure that that all the processing power of the server are dedicated to the ESB. So, what are the tests that we performed? The first experiment that we performed, and this is a very basic experiment, is we computed for the mean response time and the transaction per second as compared to the payload or the size of the ESB. So we had 6 possible payload sizes: 1 kilobyte, 2, 5, 10, 20, 50 kilobyte files. And we computed for the mean response time and transaction per second for each of the file size. Of course, it's easy to predict the result of this experiment, but well, this is our result. So in our graph, the line graph represents the response time per transaction. And obviously, as the payload size increases, the response time also increases. On the other hand, the bar graph represents the transaction per second. So obviously, again, the smaller the payload size, the higher the transaction per second. Because well, transaction per second and the mean response times are inversely proportional with one another. So basically, the result of this experiment is expected. It is also interesting to note that on a standalone basis, if we send a 1 kilobyte file to the ESB, it can process 600 transactions per second. Versus if we send a 50 kilobyte file, I think it is not shown in the graph, but it's less than 10 transactions per second. Now here, the queuing time versus the processing time. So this is an interesting experiment. We wanted to know the effect of queuing on the response time. So in order to perform this experiment, we assume that the file size is constant, so we use a 20 kilobyte file size. Also, we simulated the case where we will have 10, 20, 50, 100, and 200 concurrent users with the same number of requests with the same file size. And this is our result. So, where do we start? The broken line graph. Okay, so the broken line graph, this one, represents the average processing time. On the other hand, the broken line graph that is consists of this one represents the average response time. So we can see a significant difference. So how do we interpret this result? This means that the processing time, the time it takes for the ESB to process the message, send it to the registry, and receive a response and send back the response to the EMR, is constant, regardless of the number of concurrent users. So even if we have more users or less users, the processing time of the ESB remains constant. On the other hand, the response time, the mean response time measures the time from where when an EMR sends a request to the ESB. The request will be in the queue because we have concurrent users. We only have, I think in the setup, we only have 2 servers. And then from the queue, it will wait for its turn until an available server is present. And then The load balancer will send the request to an available server. The server will process the request. It will send the data to the registry. The registry will send a response to the ESB. The ESB will send a response to the EMR. So all of those processes are covered by the mean response time. So basically, the difference between the mean response time and the mean processing time is the time in the queue, the queuing time. So the bar graph below shows the queuing time as a percentage of the response time. We can see that the queuing time, that the percentage of the queuing time the queuing time as a percentage of the response time increases when the number of concurrent users increases. If we have 200 concurrent users, as much as 30% of the whole response time is only time is spent when the request is still in the queue. So I think this gives us an idea that we should also scale up the ESB, because if we don't scale up the ESB, the queuing time of the request will eat up the whole response time. Next, we also wanted to know the effect of the security module. So for here, we assume varying payload, so the different sizes, and we computed for the transaction time for the case where there is encryption or decryption versus the case where there are no encryption or decryption. So we wanted to know what is the overhead of the security module in an ESB. So this is the result. Well, the general pattern, of course, is the larger the data, the payload size, the lower the number of transactions per second. So we were able to conclude it during the earlier experiment. But what is interesting here, and well, it's quite obvious, the bar graph with the lighter blue line represents the transaction time with the security module. It means we have encryption and decryption. While the bar graph with the darker blue line shows the transaction per second when there is no security module. So obviously, if we will have no security module, we can process more transactions. So how big is the difference? In this graph, basically from this graph, we were able to derive this result. This shows the percent of security overhead. This is the additional time that is caused by the security module. So obviously, this increases as payload size increases. Why? Because as we have a larger payload size, the encryption takes longer because we have a larger data to encrypt, or the decryption takes longer because we have a larger data to decrypt. So the overhead increases as file size increases. We also wanted to check the effect of data formats in the ESB. So we want to know if the ESB can process JSON data faster or it can process XML data faster. Similarly, we use varying sizes, and this is our result. In the left side, the left graph shows the processing time for each payload size with varying formats. So the lighter blue represents the case when we use a JSON file and process it inside the ESB. The darker blue line shows the case when if we process an XML file inside the ESB. So looking at the left graph alone, we can see that there's no significant difference. If we further quantify the the difference, the graph in the right shows that the difference in performance between using the two form in between using XML or JSON is not significantly different. It's less than 1%. So the ESB will work whether it uses a JSON file or an XML file. Next, transformation performance. We also wanted to know if an ESB transforms an XML to a JSON file, or if there will be no transformation, how big is the difference? So again, it's significant. It's not significant, or the other way around. If we have a JSON file and we want to convert it into an XML file, the difference is not so significant. In our graph here, for file sizes less than 5 kilobytes, the overhead is less than 2.5%. What is quite significant here is this. Converting from JSON to XML takes a little bit longer than conversion from XML to JSON inside the ESB. Next, we also wanted to check the effect of validation in the ESB. So in order to check the effect of validation in the ESB, we considered two scenarios, with or without validation, and we used different payloads. And this is our result. The bar graph with the dark blue bar graph shows the scenario where there is no validation, while the lighter blue graph shows the scenario when there is validation. Obviously, the ESB will work faster if there will be no validation in the ESB. But again, we want to quantify how big is the difference. For a 50 kilobyte file, the overhead due to validation is around 33% of the whole response time. Well, obviously, it's increasing. Surprisingly, as compared to the other graph where the increase is exponential, we see here a linear increase in complexity in the overhead due to validation. On a 1 kilobyte file, the overhead is around 24% of the whole response time. It's still significant. So before I move to the next slide, we can see here how big the effect of validation is on the performance of an ESB. And we now have the next graph. So the next graph shows the contribution in terms of time of the different components of the ESB. So what can we see? Validation takes almost 1/3 of the whole processing time. Mitigation takes also a significant component, because in mitigation you need to read through the data and perform services. Translation, I think the issue in translation is if we need to send a request to a third-party terminology service and routing, because we had data to the registry. So I think the biggest insight that we can see here is 50% of the time, of the processing time of an ESB is taken by mitigation and validation. We also had fault tolerance test. So in fault tolerance test, we simulated a 10 server setup, and we recorded how the transaction per second increases or decreases if a set of server goes down. Basically, we want to measure the effect of the effect in the transaction time when a server dies or goes offline. So we have here the graph. So of course we expect that as we have more servers going offline, the lower the transaction per second is. So the bigger effect on the performance of the ESB. And basically, we have here a more or less linear output. So if we have 10 servers, so the baseline is 10, so we can have 200 transactions per second. If one server dies down, we will only have 9 servers. Automatically, the performance of the ESB reduces to 90% of its original performance. If it goes down to 2 servers, to 8 servers, it will have a significant difference. And it continues to decrease as more servers goes offline, to the point that if we only have 1 server left, the ESB can only process 10% of its original capacity. This is also another interesting slide. We wanted to compare the overhead that is caused by the ESB, because right now in the Philippine Ministry of Health, EMRs are submitting to the PHIE Light registry directly. In a scenario where we have an ESB, an EMR submits one ESB first, and then the ESB sends to the PHIE Light registry. So that is the current scenario right now. So basically, it is expected that the ESB will produce some overhead. In our graph, the bar graph, the blue bar graph shows the transaction per second, the number of transactions per second. Sorry, the graph is quite faulty. The blue bar graph shows the number of transactions per second when we are using the web service alone, PHIE Lite alone. Well, the orange bar graph shows the transaction per second when we are using an ESB. So, of course, we can process slightly more transactions when we are using an ESB, and when we are not using the ESB, because the ESB gives us some overhead. Under current workflows, the data size that is being sent, the payload size, is around 4 to 5 kilobytes. So in this graph, we can show that if we use an ESB, we will get at most 5% overhead from the existing work time. So 5% overhead is quite significantly small as compared to the benefit that can be obtained when we use an ESB. So I think I have already discussed before the benefits, and I just want to show to you how does the ESB compare to the current web service that is being used. For authentication, this is done inside the ESB. Similarly, the web service implemented its own authentication module. For queuing, this is done inside the ESB. For the web service, there is no inherent queuing. For validation, this is done inside the ESB. For the web service, this is not implemented always. For transformation, this is done inside the ESB. Again, transformation is not always implemented in the web service. For translation, aside from a third-party terminology service, the SATO ESB has a native terminology service that we can use. For a web service, for the PHIE Lite web service, it is implemented separately, and it must be connected to the web service. For routing, it is done inside the ESB. Well, for the web service, it is also done inside the web service. For implementation, the ESB provides a single point of entry. On the other hand, if we continue using the PHIE Lite registry component, new registries must have new set of services. So the 5% overhead that we got if we use the ESB is actually being justified by the benefits that we will obtain when we use it. So basically, that's the that's the just to summarize, we perform functional testing, integration testing, and performance tests. So the performance tests were able to give us benchmarks on what to expect when we use an ESB. The integration test proves to us that the ESB can work in a national context. Well, the functional testing shows that all the functionalities that were specified during the requirements gathering phase are satisfied. So basically, the end of the webinar series, the 3 webinar series that we presented. So we presented the experience of the Philippines in implementing a prototype health enterprise service bus. Do you have any questions?
Philip, this is Carl. Thank you for thanks for the detailed presentation on that and a lot of information there. I've got Richard and Linda here who have been following very attentively to the pattern and methodology you've used. Request is, could these slides, the slide deck, be made available for download either in a PDF or PowerPoint? So we can have a look at that.
I will be giving it to Cherish later.
Fantastic. I think that's great.
Thanks very much. That was a great presentation.
Thank you.
Philip, now this is the results of what you've looked at going forward. Is there any plans to have this as an ongoing evaluation framework for new technologies that the SIL is looking at?
I think at the lab we are currently documenting the results that we had earlier, and then I think within the next 2 months we should be able to announce a framework and an environment on how we can test various technologies, or how other countries, because other countries might want to use the framework, it will also be made available. So either we do the testing or another country does their own testing.
Fantastic. I think I'm going to put Jamie's hand up here. We'd like to work a little closer with you, and there's email in your inbox introducing Richard to you, who's working very closely with me here. We'd like to see how we can implement some of these and see how the OpenHIM performs against this as a standard way of representing our testing results.
Yeah, sure, yeah, of course.
Perfect. Are there any other questions from the community?
I think there's no more questions.
There are no more questions, Sir Philip.
Okay, thank you.
All right, well, thank you, everybody. I know we've had a short few attendees today, but this has been a fantastic presentation, and I know our team in Cape Town learned a lot from it. We'll definitely push this out into the OpenHIE list itself. Philip, just to check, I don't have my paper in front of me. Is there another presentation on the back of this to wrap up the ESB discussion, or is this the end of your series?
I think this is the end of my series. The next talk, I don't know the schedule yet, is on the costing tool on how we can cost OpenHIE implementation. So this is, the next talk is not very technical.
Fantastic. I think we're really looking forward to that. I know in Cape Town particularly that's a question we're always asking. So I think we've sort of lockstepped in and out of our scheduling here. So the next AeHIN hour will be on which date, Cha?
The week after next, Sir Carl. It's the week of the 16th.
That's the 16th around, I believe.
Therese?
Yes, sir.
August 16 will be the launching of the lab.
Alright.
Carl, we are launching Hyla in the Philippines on August 16.
Congratulations. Well, let's have the next call then on the 23rd of August, and then we realign ourselves with our agenda.
Yeah, sure, yeah.
Fantastic. Great.
Okay, thank you.
Right, thank you everybody. That was fantastic. The next call will be on the 23rd. And Philip and Chad, that's really exciting. And please send us some photos of the launch of the lab. I'm personally looking forward to seeing that.
We will be making it available online to Carl.
Great. Well, thank you everybody for your time today. Have a great day, and we'll see everyone in cyberspace.
Okay, thank you, Carl.